Hello everyone and welcome to Reinforcement Learning Tutorials. In this tutorial, I will explain the Monte Carlo method for learning state value functions. In particular, I will explain the first visit Monte Carlo method. Everything explained in this video can easily be generalized to many visit Monte Carlo method for learning state value functions. What you can see over here is a Python code file I developed that implements the Monte Carlo method. Over here, you can see a Frozen Lake OpenAI Gym environment that is used to test and to analyze the performance of the Monte Carlo method. I will teach you how to generate this simulation and how to write this code over here. Before I start, I would like to mention a few important things. First of all, those of you who follow my work or who are my subscribers know by now that I always create a post that nicely summarizes everything that I will explain in this video. And consequently, here's the post. This post contains explanations, equations, graphs, and the Python code. A link to this post is given in the description below. Then it took me a significant amount of time, energy, planning, and effort to create this post and this video. Consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Before watching this video or reading this tutorial, it's a very good idea to first obtain enough background information and knowledge so you can understand the material presented in this video tutorial. Consequently, I suggest you that you go over these three tutorials. For example, if you click on the first tutorial, you can learn more about state transition probabilities, actions, episodes, and rewards. Then, if you click over here, you will come to the page explaining installation and getting started with OpenAI Gym. This is a very important tutorial that will help you to get familiar with the OpenAI Gym. Then, the third tutorial is dedicated to value functions and Bellman equation. Of course, if you're familiar with these three topics and if you have enough background information, you can simply skip these three tutorials and proceed with this video. Monte Carlo method is a model-free method for learning the state value function. Under the term model-free method, we understand a method that does not require a priori information about the state transition probabilities. That is, Monte Carlo will learn the model of the environment. First of all, we need to recall the definition of the state value function. The state value function is defined by this equation over here. V is the notation for the state value function. S is the current state. Capital ST denotes a state at the time step t, where t is the time step. GT represents the return, and the return is defined by this equation over here, where R t plus 1 is the reward obtained at the time step t plus 1. So to summarize, the state value function represents a mathematical expectation of returns obtained if we start from the state S at the time step t. And I forgot to mention that pi over here is the policy that our agent is following. So we can imagine an episode or a sequence of states and rewards that looks like this. We start our journey at st is equal to s, where s is a particular state, and we follow a policy pi. And this policy will generate a sequence of future states and future rewards. Consequently, we can have something like this. ST1 is the next state, RT1 is the reward obtained at the next state. Then we step further. ST plus 2 is future state, and the obtained reward is RT plus 2. And consequently, this process goes on until the end of the episode. That is, until we reach a terminal state. The return at the particular state is simply a weighted sum of obtained rewards. So you take the rewards until the terminal state and you simply sum them up by taking into account this weight over here that's called a discount rate. We can clearly observe that the state value function is a mathematical expectation, so keep in mind that fact. That's very important for the future developments. The state value function is a mathematical expectation. Roughly speaking, the expected value can be seen as a value obtained by repeating a random experiment an infinite number of times and calculating an average value of the values observed during each random experiment. So expected values eventually will converge to averages. That's very important to keep in mind. Motivated by this, the main idea of the Monte Carlo method is to simply run many episodes and observe the corresponding state trajectories and obtained rewards. Then, on the basis of this information, the Monte Carlo method approximates the state value function as an average return of the returns observed in random episodes. Let us illustrate this idea graphically. Consider the frozen lake environment shown over here. The frozen lake environment is a 4x4 grid of fields. Here are the fields. This is the first field, second field, third field, fourth field, and this is the 16th field. To every field, we associate a state. And the states are denoted by S1, S2, S3, S4 until S16. This state, S1, is the starting state. And this state over here, S16, is the terminal state. An agent follows a certain policy. Its goal is to come from this state to this state over here. We can move down, left, right, or up. By going from one field to another, we obtain a certain reward. For example, if we are in this field, that is, we are in state S4, and if we take action left, we will end in this field over here, that is, in the state S3, and we will obtain a reward of R3. Similarly, if we are in the initial state S1, and if we take the action down, we will go to the state S5 and we will obtain the reward of R5. An episode is a sequence of states, actions, and rewards obtained by following a certain policy. In the graph over here, an episode is represented by this red trajectory. We start in the initial state, and by following a certain policy, we obtain this trajectory and we end in our terminal state. This red trajectory can be represented by the sequence that you can see over here. Note here that capital letters, that is capital letter S with an index t, represents a state at the time step t. Consequently, S0 is the state at the time step 0, and it is our initial state S1. Then the state at the time step 1 is the next state S5. Then the state at the time instant 2 is S6, etc. Each occurrence of the state, lowercase si, in an episode is called a visit. So going back to our episode, we can see that we visited S1, S5, S6, and if we go further, the final visited state is S16. We also obtain rewards by going from one state to another. The obtained rewards in the sequence or in an episode are R1, that means that this is a reward at the time step 1 is R5. So let's go back to our graph and let's see that. Going from the state S1 to the state S5, we obtain the reward of R5. Then, going from the state S5 to the state S6, we obtained the reward R6. And here are the rewards in the sequence. This is R5 and this is R6. Let us for a moment assume that the discount rate is gamma is equal to 1. Since we only have a single episode, the average return for every state will be equal to the return obtained at this single episode. For example, on the basis of only this single episode, we obtain the following estimates of the state value functions by using the Monte Carlo method. The state S1 is the state at the position S0 in the time sequence. Consequently, we have the value function at the state S1 at the time step t is equal to 0 is equal to the sum of future rewards until the terminal state. So going back to our episode and substituting these values for R1, R2 until R12, we obtain the return at the state S1. And this is actually an estimate of the state value function since we only have a single episode. On the other hand, let us focus on this state S6 and let us estimate its state value function on the basis of a single episode. We can see that this state is visited twice. First of all, it's visited when we go from S5 to S6, then we go like this, and when we reach S10, we can see that we visit this state once more. So the question is how to compute the return of S6. To summarize, the state S6 is visited twice in the sequence. First time at the time step t is equal to 2, and then at the time step t is equal to 8. The main question is, what time instant or what visit of S6 should be taken into account when computing the return? In the first visit Monte Carlo method, we compute the return starting from the first visit of the state in the sequence, that is, starting from the earlier time step. We count the return starting from the time step t is equal to 2. When we reach S6 again later in the sequence, that is at a time step t is equal to 8, we also count again the reward obtained by visiting the state S6 for the second time. And that's the main idea of the first visit method. Consequently, the state value function of S6 is given by this equation over here. Up to now, I explained you how to compute a state value function only on the basis of a single episode. Let us now try to generalize this principle. Let us assume that we have another episode. That is, we generated another random experiment. In the second episode, we observe the rewards and compute the return from every state in the sequence by using a similar strategy. We also count the number of first visits to the particular state. Then, we add these returns to the corresponding returns from the first episode and divide the result by 2 if the state is visited in this episode. We repeat this process for future episodes. And in this way, we average the return for every state in order to estimate a state value function. Up to now, I explained how to compute state value functions only on the basis of a single episode. Let us try to generalize the previously explained Monte Carlo method. In the second episode, we observe the rewards and compute the return from every state in the sequence by using a similar strategy. We also count the number of first visits to the particular state. Then, we add these returns to the corresponding returns from the first episode and divide the results by 2 if the state is visited in the episode. We repeat this process. Generally speaking, if we have n episodes, for every state, we sum the returns in every episode and obtain a total sum of returns. Then we divide this sum of returns by the number of times a particular state was visited for the first time during these n episodes. The result will give us an estimate of the state value function for the particular state. Let us explain this principle graphically. Let us say that we performed 3 experiments and that we generated 3 episodes that are shown over here. Episode 1, Episode 2, and Episode 3. Here are the 3 trajectories, the state trajectories. This is the first state trajectory, this is the second state trajectory, and since this is a random process, the state trajectory in the third episode will not look the same as the state trajectories in the previous episodes. Let us first estimate the value function at the state S1. The returns from the state S1 for these 3 episodes are. Let's focus on the first episode. The return from state S1 in episode 1 is R5 plus R9 plus R13 plus R14 plus R15 and plus R16. So this is the return for the first episode. For the second episode, obviously we have R5 plus R9 plus R10, R11 plus R12 plus R16. And finally, in the third episode, we have R5, R6, R7, R11, R15, and R16. We also keep track of how many times the particular state S1 is visited during these 3 episodes, and it's visited 3 times. Consequently, we compute an estimate of a state value function by taking the return from the episode 1, then adding the return from the episode 2, and finally adding the return from the episode 3 and dividing the result by this number 3 that represents the number of times the particular state, in our case S1, is visited during these 3 episodes. And that's the principle. That's the basic principle for estimating a state value function at S1. Next, let us estimate the state value function at the state S9. Let us see this state on our graph. It's over here. Here's the state S9. We can see that this state is visited in the episode 1 and in the episode 2. However, this state is not visited in episode 3. Taking this information into account, we can obtain the return for episode 1. It's R13 plus R14 plus R15 plus R16. We can see on our graph these rewards. If I zoom out a little bit, and we can see over here. We're here, right? And we look further, starting from R9. So we see it's R13 plus R14 plus R15 plus R16. This is the return. Then the return in the second episode is again, we start at this particular state and we look at the future. And we have R10 plus R11 plus R12 plus R16. The state S9 is visited 2 times. It's visited in episode 1 and episode 2. So we take the return from the episode 1 and we add this return to the return from the episode 2 and we divide the result by 2 since this state is visited twice. In the sequel, I will present a Python code for implementing the first visit Monte Carlo method. The main idea goes as follows. First, we need to create vectors that store total returns and total number of visits for every state during simulated episodes. Then we create a for loop that will in every loop simulate an episode. This loop should generate episodes and trajectories. So in the first iteration, we obtain this episode. In the second iteration of the for loop, we obtain this episode. And in the third iteration of the for loop, we, for example, obtain this episode. Then, in every episode simulation, that is, in every iteration of the loop, we need to compute the return for every visited state. For example, if in the first episode we visited this state, and this state, we need to compute the returns from every state. For example, for this state, we need to take reward over here and the reward over here. And similarly. Then, in every iteration of the loop, we need to update the vectors that store the total return and the total number of visits for every particular state. After the loop is completed, we divide every entry of the vector storing total returns by the number of visits of a particular state. So let's try to implement this in Python. Here are the Python code files that I develop and that implement the first visit Monte Carlo method for approximating the state value functions. I developed 2 files. The first file is a driver code that's higher level code, and this code calls functions in this file functions.py. Here's the function that implements the Monte Carlo method. The input arguments of this function are: first input argument is the OpenAI Gym Frozen Lake environment. The second argument is the number of states. The third argument is the number of episodes that we will simulate, and the last argument is the discount rate. Then inside of this function, I first import the NumPy library. Then I define, or better to say, I declare these 2 vectors. The first vector stores the sum of returns for every state during the episodes. The second vector stores the number of visits of every state during episodes. Then I declare this vector called value function estimate, and this vector is the final result that's returned by our function. Then over here, I loop through episodes. In this for loop, I generate random episodes. First of all, I initialize a list that stores visited states in the current episode. Then I initialize a list that stores the return in every visited state in the current episode. Over here, I reset my environment, resetting the environment actually means that we return our environment to initial state. That is, in every episode, we return our environment to S1, since we start from here. Then, over here, I append the list of visited states by the current state, and the current state is actually the initial state, S1. Then I print this message that will simply inform us we are simulating episode 1, 2, 3, etc. Then, in this while loop, I simulate an episode. Here I have true, which means that this should be an infinite while loop unless something happens. That is, unless I reach a terminal state. And when I reach a terminal state, I will break this while loop. So inside of this while loop, I first select a random action. I call this function action space sample. This is an OpenAI Gym function. This function will basically create a random action, and the actions are 0, 1, 2, 3. They can be down, left, right, and up. Then over here, I step inside of my environment, and I say to OpenAI Gym, step according to the generated random action. This function, step, will return the state, that is, the state that we go to. It will return the obtained reward by reaching that state, and it will return us this Boolean variable that is used to investigate if our state, that is, if our destination state, is a terminal state or not. If this terminal state becomes true, then we know that we reach the terminal state. Over here, I append the obtained reward. Then I go further. I investigate if the current state that we went to is not or it is a terminal state. If it's not a terminal state, I simply append the state. Otherwise, I break the while loop. Let us explain this further. Let us say that a state sequence is given over here. S0, S4, S8, S9, S10, S14, and S15. Then this vector, visited states in episodes, will be 0, 4, 8, 10, and 14. And note over here that S15 is the terminal state, and this state is not included in the list. The return vector is then R4, R8, R10, R14, and R15. Now that we finish an episode, we need to count. So first of all, I need to count how many states we visited. Then I initialize my return to 0. And over here, I need to compute a return for every state that's in this sequence, visited states in episodes, and I need to count how many times a particular state is visited. Now, to do that, we will use one trick. Instead of going forward, we will go backwards. And the main idea is to compute this return in the most efficient manner. We can see that we can decompose the return as this. And this equation can be implemented as follows. First of all, we initialize return to 0, and then we perform backward summation. So for example, if we have a sequence of rewards that's basically R1, R7, R10, R11, and R14, we will do the summation backwards. We will start from R14 over here, and we will sum the values in a backward manner by adding this weight over here, gamma. That is, by summing up and by multiplying the return by gamma. By using this principle, we can compute the return for every state in computationally efficient manner. So over here, we start our loop backwards. We go from the last visited state and we go backwards. Then we assign these two values. We compute the return. And over here, we check if the state that we visited is the first time we visited this state or not. If it's not the first time we visited, we don't do anything. We wait until this state is visited for the first time. And after we finish that, this part of the code, we complete one episode simulation and we go back to this for loop and we repeat the episode simulation again and again until we reach the number of episodes. Once we reach the number of episodes, we basically sum the total number of returns divided by the number of visits, and we obtain a state value function for every state. And finally, we return the value function estimate. Okay, so let's see how this function works in practice. First of all, I need to import the necessary libraries. I need to import the gym library and I need to import the NumPy library. Then from my functions file, I need to import the functions I developed. Besides this function, I need to import two additional functions. The first function is called evaluate policy. And here is this function. This function is used for comparison. And this function implements an iterative policy evaluation algorithm for approximating the state value function. I created a separate video and tutorial that explains this method. You can find this tutorial by going on my website, and over here under the menu Machine Learning Data Science, you can find all the reinforcement learning tutorials. And the tutorial that explains the iterative policy evaluation algorithm is given over here. I strongly suggest you that you go over this tutorial. Besides evaluate policy function, we also need to import the plotting function. This plotting function will plot the computed state values on a 4x4 grid. The next step is to create our environment. Over here, I will create a custom Frozen Lake environment. S denotes the starting point. FFF denotes the frozen lake. This is the first row, this is the second row, this is the third row, and this is the fourth row. H denotes the hole, and G denotes the goal state. So let us create the environment and let's render this environment. In this code line, we create the environment, then we reset the environment and we render the environment. And let's see the result. Here's our rendered environment. We start from this point over here, and here's the goal state. The frozen states are given over here, and this is the whole state. Now, we can run the Monte Carlo simulations and keep this environment open. So let's do that. First of all, we assign the state number. We call this function observation underscore space, and we select n to obtain the state number. Then we select the number of simulation episodes. We assume 10,000 of simulation episodes. We select the discount rate and we call our function. And let's see the result. Okay, Message, simulating episode 0, simulating episode 1, and let's see what's happening. Okay, so here's the simulation. So this is an episode, we started from here, and there are two possibilities. Either we will end here, or we will reach the hole. And let's see what will happen. You can see that it takes quite some time to simulate one episode, and remember that we have 10,000 of episodes, and let's see, maybe in 5 or 10 seconds will we reach the terminal states. The terminal state can be this state or this state, and let's see what will happen. Okay, so this was one episode. Since it takes quite some time to simulate a single episode while rendering, I will simply press the Ctrl+C to cancel my simulation, and over here I will run the simulation without rendering the environment. We can do that by first closing the environment by typing end close, and the window disappears. Then I will comment this code line, and I will use an alternative environment. This function will do the same, except for the fact that we will not render the environment while creating the environment. So let's do that. Let's run the code again, and let's run our Monte Carlo simulation. And you can see over here, we can see the message simulating episode, and maybe after 5 seconds we reach the end. We simulated 10,000 episodes, and here is the returned value. This vector represents the state value functions for particular states or fields. Now, let us compare the results with a previously used function, and that previously used function implements the iterative policy evaluation algorithm. First of all, we need to select an initial policy. This initial policy will not change during the simulation. It will be a complete random policy. That is, in every field of our Frozen Lake environment, we have equal chances of selecting up, down, left, or right. Then we initialize the value function vector. We select the maximum number of iterations of the iterative policy evaluation. In our case, it will be 1000. Then we select the convergence tolerance. So let's run this function, and let's see the result. Okay, iterative policy evaluation algorithm converged, and notice here that the iterative policy evaluation algorithm uses a model of the environment to compute the state value functions. Let's plot the result. First, we'll plot the result computed by using the iterative policy evaluation algorithm. Let's see the result. Okay, so this grid represents state value functions at particular states. This is state S0, and the state value function is 0.43, and this state is S14, and the state value function is 0.65. So this is our baseline. This is the most accurate result. And let us see what our Monte Carlo method is giving us. Wow, let's compare the results. And we can see that the Monte Carlo method gives us almost the identical results. Almost identical. If we increase the number of simulations or number of episodes, these two results will perfectly match. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.